Hi everyone. Thank you for joining the webinar. My name is Vikram and I work for GL Communications. So this is our webinar on air traffic management test solutions. And I'm joined on this webinar by three of our senior engineers, Rob Bishevsky, Srinivas Balulad, and Nagaraj. And we are very excited to talk about this topic with you here today. Um, we have cutting-edge solutions for air traffic management testing, voice quality, latency measurements, compliance and conformance, and so on and so forth. So we have a whole host of solutions designed to test these mission-critical networks, and that's what we are very excited to talk to you about here today. So I think a lot of you are already familiar with GL Communications, but if you're not, we've been around since 1986, and we are a telecommunications consulting company, and we also manufacture telecommunications test and measurement equipment. We are headquartered in Gaithersburg, Maryland. We also have a development office in Bangalore, India, as well as sales representatives working all around the world. So our test and measurement equipment covers the full spectrum of different telecom networks. We can interface to wireless networks, VoIP networks, air traffic management networks, which we're talking about today, fiber optic networks, legacy networks like TDM, T1E1, T3E3, and analog networks as well, like the legacy public switch telephone network and so forth. So we can connect to pretty much any type of interface, any type of telecom network that you're interested in testing, and we can do a whole plethora of different types of testing on those networks. We can monitor the networks, and we can also emulate traffic on those networks. We can also test conformance to different protocol standards. Our solutions can help you visualize the network, capture traffic over the network, store the traffic. We offer portable and rack mount solutions. And as you talk to us, you'll realize that our solutions are very cost effective and just very versatile as well. It covers a lot of different types of scenarios. Okay, so we're here today to talk to you about our testing solutions for the air traffic management industry specifically. As many of you know, the whole industry is migrating to VoIP. So all the legacy networks, whether they're T1, E1, 4-wire, E&M, all those type analog networks, all of those legacy networks are being phased out, and everybody is migrating to VoIP. But this migration is not easy. It's not trivial. There has to be extensive testing done. As we know, these are mission critical networks. You have pilots and passengers in the sky, and the pilots need to be able to communicate to the air traffic control towers and vice versa. So the air navigation service providers must rigorously test all of this infrastructure for reliability, stability, interoperability, all sorts of different performance metrics, and so forth. During this migration, you'll find that a lot of these legacy networks still must be maintained and remain in use. So always keep in mind that we have solutions for testing both the legacy as well as the VoIP portions of these networks. Now, GL is at the forefront of all of this. We work with many air navigation service providers. We work with equipment manufacturers, government agencies, contractors, and so forth. GL is a member of EUROCAE, and we contribute in Working Group 67, and so forth. So we sell our solutions. We do consulting services as well throughout the whole air traffic management industry. Here's a quick depiction. You have your controller working positions where your air traffic controllers are sitting, and the voice communication switches are there at those air traffic control towers. And then you have your actual remote radio stations, which are communicating to those air traffic control towers and then relaying those signals wirelessly up to the planes in the sky. So we can test over the wired portions of the network. So from the ground radio stations to the air traffic controllers, all of that is wired infrastructure, and that's where our test equipment sits and does its analysis and monitoring and emulation. We are compliant with all the latest standards, ED 137B and C. As you know, ED 137 is based on VoIP, but it's tailored specifically towards air traffic management. We also do ED 138 for monitoring. We do delay measurements, voice quality testing. Our solutions are voter validated, for those of you who are familiar with voter. We're going to talk about here today, we have a whole bunch of solutions that we want to talk about because everybody is interested in something a little different. First off, we can emulate. We can emulate ED 137 traffic. We can do, as you know, ED 137 has standards for radio, for telephone, and for recorder interfaces. And we have a very flexible, versatile software program called MAPS, which I'll describe momentarily. And this software program can emulate the ED 137 standard. And we'll talk more about it momentarily. Now, we also can monitor according to ED 138. We have two solutions for monitoring. They work together. One solution is called Packet Scan, and the other solution is called Net Surveyor Web. Now, all of these solutions are software-based, but we can always incorporate them on rack-mountable PCs or portable platforms if you need high-performance computing, if you're capturing high volumes of traffic or capturing for long periods of time at high data rates and so forth. We have specialized hardware which can work in tandem with our software to make sure that we can capture all the traffic, not miss anything, process everything in real time without issue. In the later half of this presentation, we'll talk about delay and voice quality measurements, how we generate the traffic, and then how do we will generate audio traffic and signaling traffic, and then we use our specialized hardware that all works in tandem to do all these sophisticated measurements, such as voice quality, signaling delay, audio delay, and things like that. So that's what we're going to talk about: emulation, monitoring, and then specific measurements of interest. Let's start with our program with our emulation solution, MAPS. MAPS is an acronym. It stands for Message Automation and Protocol Simulation. It's here down at this last bullet right here. Message Automation and Protocol Simulation is what we call it. Some of you may know our other MAPS programs. We can simulate many different telecom protocols: SIP, RTP, analog, TDM-based protocols like SS7, ISDN, so on and so forth. We can actually emulate a whole host of different telecom protocols, but today we are going to focus on ED 137. Now, this software program MAPS can be deployed at the air traffic control towers at the controller working position and simulate an actual controller working position. You can do everything that the actual air traffic controller can do. You can trigger PTT, push to talk. You can talk. You can send audio across. You can do various types of signals, main standby transfers, and things like that. So it's all possible with our software program. It's basically indistinguishable from a actual controller working position. Now, again, we're showing here just the IP portion of the network because we're focused on this VoIP migration. So everything here now is going over IP, and at the other end, you can have another controller working position that's simulated with the GL Maps tool, and so you can do an end-to-end call. This would be a ground-to-ground call using ED137 telephone protocol. So it's a full end-to-end call, ground-to-ground, and you can send audio bidirectionally and do the measurements bidirectionally. Now, you can also go from the controller working position out to a ground radio station. So that would be an air-to-ground call. And again, the GL Maps tool will emulate that ground radio station. Everything that the radio station can do, the GL Maps tool can also do. It's indistinguishable. So you can emulate the air-to-ground call, send audio both ways, do all types of signaling, squelch breaks on, squelch break off, that type of stuff. It's all doable. So and it's just a software program. Very simple, easy to use software program. You install it on a Windows PC and you're off and running. And then for monitoring, again, we use our Maps ED137 recorder software that's sitting somewhere in the centralized network. And this recorder is doing just that. It's recording all of the air traffic that's taking place and saving it for future use, for future analysis, and so on and so forth. So all of the VoIP traffic is now being saved to this VoIP recorder, and we can simulate the VoIP recorder with our Maps tool. So that's where we sit in the network, pretty much everywhere on the wired path. We don't touch the wireless path, so we're not going to be in the plane. But on the wired portions of the traffic, that's where the GL Maps tools sit. The Maps software, no matter what protocol you are emulating, the Maps software is very easy to use. It's very user-friendly, and it looks the same. Whether it's ED137 radio, whether it's ED137 telephone, recorder, or basic SIP, or ISDN, or anything else, it's the Maps software looks exactly the same. It has a nice, easy-to-use graphical user interface. You can start and stop calls. The calls are fully configurable, and you can see the entire call setup and teardown. So every important event that takes place on the call, you can see it right here in the ladder diagram. You can actually simulate hundreds of simultaneous calls, simultaneous air-to-ground calls, with the click of a button. And every air-to-ground call is fully customizable. So every air-to-ground call can have its own profile. So you can call out to different ground radio stations, different controller working positions, so different IP addresses, source IP addresses, destination IP addresses, different audio payloads and codecs, and different call durations, different events. Every single call is distinct, and every single call is customizable. Really quickly, I'll also mention that we have support for Python scripting. We can also provide Python APIs. So if you're doing more advanced testing where you don't want to click over and over again, you don't want to click buttons over and over again, You can do repetitive testing or regression testing through simple Python scripts. We provide you with sample Python scripts to help you get started, and we can also help you write the scripts. So that's one of our key advantages, is the fact that we also support scripting, so that you don't have to sit there and click buttons. You click a button once, and then the script runs through all the scenarios you're interested in and gets all of the results back to you. So through the power of scripting, you can do pretty much anything, any type of testing you want. Let me go ahead and turn it over to Srinivas.
Yeah, thanks, Vikram. Hello, everybody. Okay. So as you can see on this slide, we can emulate the controller working position or the ground radio station. Okay. So all the emulation is as per the AD137 B and the C versions of the Volume 1 radio interfaces. Okay. So the advantages of our emulator is we can simulate hundreds of controller working positions or the radios in a single instance of the software. I mean to say, like in a single license. So that makes life very easy by wherein you can configure all your required controllers for the test in a single window. Okay, and our emulators have been designed to cater different needs of the testing phases. For example, right from the functionality testing, load testing, regression testing, it can even go to the FAT testing, like a deployment testing, field testing. Okay, and you can even perform a lot of negative testing also. Okay, so that is how the product has been designed to cater. Okay, and we can simulate all the call types, radio call types, PTT types, and we can even configure each and every parameter in the SIP, SDP, and ED137 parameters mentioned in the specifications. Okay, and we also simulate the advanced features like link session management, multicast routing, and all. Okay. And recently we have enhanced our emulators to support IPv6 addressing, and we have also validated against the older versions, the latest versions 4.1.33.1 and 33.2. So as you can see on this slide, okay, we are simulating 10 controller working positions. Each controller working position can be configured with all these parameters, be it be like a SIP addresses or a wide range of ED137 parameters. For example, what is the radio call type, radio TXRX, radio idle, and we can configure the PTT types, frequency like this. Okay, so uh, we can even do the quick configuration to configure hundreds of controller working positions also. Okay, and apart from that, we can simulate all the four RTP header extensions specified by the specifications. Basically, they are like climax time delay, signal quality index, radio remote control, and dynamic delay compensation. Okay. And once we simulate these A to ground calls, we can do a different kind of traffic actions. For example, we can send and record the audio files. We can send and detect the digits and tones, or we can also talk using the microphone connected to the system, or we can play the audio to the speakers. Okay, and apart from that, we can also apply some impairments to the generated traffic. For example, we can introduce packet loss, duplicate, out of sequence, and latency. Okay, and we do support codecs like ALAW, ULAW, and G729, which are widely used in this domain. So here on this screen, calls have been received at different ground radio stations emulated. Okay, and it will also show like what are the controller working positions. As Vikram mentioned, like there is a call graph which can uh, list out all the important activities that are happening along with the timestamps, and we do get the message decode of every message. And you can see here some of the action buttons where using which you can perform like start squelch, apply a signal quality index, or turn on the PTT summation, something like this. Okay, and We support all the call preemption, priority handlings, and all. We can even simulate the combined and separated radios. Okay, and apart from that, we can simulate like hundreds of A to ground calls along with the automated traffic actions like keying the PTT and the squelch actions automatically on the established calls, which will help in performing the load test and the regression test on the device or the network. So as you can see on this screen, okay, so we are using two instances of maps. One is to simulate the controller working positions. Other can be used for the simulating the ground radio stations. We can create multiple CWP and GRS profiles, and we can do all kinds of radio call types like radio idle, TXRX, receive only. Okay, so this is what the advantage of the maps framework. So on this slide, we are listing out few of the important C features which were introduced by the ED137 C version specifications. Basically, these include like radio receiver multicast operation simulation, selective calling tone transmission, and also reporting about the frequency ID changes at the radio, and even to keep the active sessions live even if the frequency ID changes, and simulating the one more PTT type, that is a test PTT. So that all those slides summarize the radio emulator. Now we are moving to the telephone emulator. Okay. Telephone emulator, basically it emulates the ground to ground calls as per ED137 volume 2 telephone interfaces. Okay, and since we are using the same framework maps, so all the other features remain same, like the flexibility Python APIs or easy to use graphical interface and all. Okay, and on the screen you are also seeing this ground to ground call, DAIDA call, along with the details like how much call time it took to set up this, establish this call and all. Okay. So basically, in the telephone emulator, we are going to simulate the controller working positions as per ED137 B and C versions of the Volume 2 interface. Okay, and we can simulate hundreds of controller working positions to simulate hundreds of ground-to-ground sessions. Okay, and optionally we do support the few of the addendums. This telephone specification has few of the addendums. Okay, out of those things, rightly currently we are supporting like FA legacy telephone networking, that is addendum 2, addendum 4 override calls, and addendum 5 voice calls are supported. And telephone emulator is also enhanced to support IPv6 addressing, and it is also validated against voter version 4.1.33.3. So again, we are taking example of simulating 10 controller working positions here. Each controller working positions again can be configured for different ground-to-ground or the telephone parameters as per the ED137 specification. And one more advantage of these things is we are providing all the default values, possible values specified in the specification. But if you want to define your own custom value or some negative values or invalid value to create, see how the device under test is going to behave for these improper values, we can easily configure and create those scenarios. Okay. And apart from that, similar to those negative testings, like I can manipulate the SIP and SDP messages to see how the other end behaves whenever we encounter the malformed messages. And we can also simulate all the SIP errors like 3xx, 4xx, 5xx, and 6xx errors. Okay. And again, we can also introduce the impairments. And apart from that, this ground-to-ground calls have a different types actually. IA, DIDA call, monitor call, override calls, voice calls, and all. All those call types are supported, and also the call scenarios like call hold transfer, call pickup, call intrusion. All these call types can be simulated along with the conference calls. So in this screenshot, we are showing like one of the air to ground call, which is established. And apart from that, we are also trying to show the different features that comes with the call generation capabilities. For example, we can run the scripts for multiple iterations or infinite iterations. Okay, so as and when the iterations progresses, we also provide the updates like how many iterations have been completed, and we can run multiple scripts either simultaneously, sequentially, or randomly. Okay, and again we can simulate hundreds of ground-to-ground calls, and we can also have a scheduler which can run a particular set of scripts or calls at a particular time based upon whatever the time we have scheduled. So this is again one more a pictorial depiction of how we can create multiple controller working positions, and we can generate hundreds of calls, different types of ground-to-ground calls. So with that, those slides summarize the features of telephone emulator. Now we are heading towards the recorder emulator. So again, this recorder emulator is going to simulate the recording sessions, either acting as a client, for example, as a controller working position or the ground radio station, or it can even act as a radio recorder servers itself. Okay, so uh, yeah, and again, all other features remain same. And on the screen, you can see this RTSP messages exchanged for a particular recording session, and the complete decode of the messages on the right side. So you can see here the recorder emulator. Basically, it can either act as a CWP, GRS, or we can even act as the recorder itself. So basically, we are simulating only the RTSP sessions required to establish the recording sessions, either as a client or as a server. And the specification actually defines three different types of transport types for the audio, and these are basically like independent TCP, independent UDP, and interleaved, which is like a embedded binary data. All these three types of transports are supported, and here also on the recorder emulator we support IPv6 addressing, and it is validated against voter 4.1.33.4. Okay, on this slide here, we are trying to show some of the use cases. So on this slide, we are actually trying to emulate the recording clients either as a CWP or as a GRS, and we can simulate the A to ground or ground to ground call recording. Okay, so for example, a recorder vendor can use our emulators to simulate these clients. We can, as I told, like we can simulate n number of like hundreds of clients, and create hundreds of recording sessions towards the recorder to do the functionality testing and also the performance and regression testing on the recorder. So here in this slide, we are actually emulating the recorders itself, and the CWP or the VCS and radio vendors can actually test their recording interfaces by emulating the recorders. Okay, so this recorder again we can emulate hundreds of recorders, and we can do all kind of like connect multiple clients and to different recorders, and perform both functionality and load testing. So on the recorder emulator also, we can create multiple CWPs or the GRS profiles or the recorder profiles. Okay, and each and every one can be configured independently. We can even create custom properties and operations. We can add it quickly to the messages. As a recorder server, we can record the audio, or we can play back the audio on that received session to the speaker. And for every call, we are going to record the call record data to the CSV file. And we can also have automated scripts. By default, with the installation, we provide some of the commonly used automated scripts which can simulate the PTTs and the squelch actions on the recorded sessions, so that they can be readily used for performing load and regression testing. So here we are going showing some recording sessions. Okay, as I told with respect to the telephone, here also we can run multiple sessions for multiple iterations. We can run the scripts simultaneously, sequentially, randomly. So hundreds of recording sessions can be emulated, and we also provide detailed call graphs and message decodes for every session here. So that concludes the recorder emulator. And on this slide, we are trying to provide some key updates related to the emulators. Okay, basically our emulators support both B and C versions, and they are constantly enhanced to support all the change 1 and change 2 features as and when they are released by the EUROCAE. Okay, and all the emulators support both the B and C versions. So when you invoke the application, you can choose either you want to emulate as a B version or a C version interface. And all our emulators support are enhanced to support both IPv4 and IPv6 addressing. And emulators are also validated against the latest voter tool. And GL actually participated in the FAA VoIP interoperability event back in 2019, which was conducted by the FAA, wherein actually all our test equipments used by all the participating vendors very rigorously. Okay. And we also plan to participate in the upcoming VoIP in ATM over IPv6 flood test, which will be there in France in September 2024. So this is how we are keeping us committed to the industry by catering the required, by enhancing our products continuously and catering the requirements.
Okay, all right. Thank you very much, Srinivas. So now we're going to talk about our monitoring solutions. Srinivas talked about our emulation solutions. So now let's talk about our monitoring solutions. So we have two different solutions, but they work in tandem. The first solution I'm going to talk about is Packet Scan. So Packet Scan is a software program. It's basically a probe. It's like a network probe that can sit anywhere on the wired Ethernet network and capture traffic. It is a protocol analysis software similar to Wireshark, but way more powerful, especially in the field of ED137 analysis. Packet Scan. So here in this figure, we have it deployed in multiple places. We have it deployed at the controller working position, so it's going to capture traffic and in real time do the analysis for you of the ED137 calls. It's going to build the call detail records. It'll compute metrics on the call, like packet loss, mean opinion score, and call setup, call teardown, call successes, call failures, things like that. As well as it can save the actual packets, it can save the actual audio of the calls. It can do a lot of different things for you. Now we're also showing it here at the IP radio station. So again, Packet Scan can be deployed there as long as there's any sort of Ethernet interface where it can connect to. Typically, you have the host PC connected to a monitor port on a switch, and that's how it's capturing the traffic. And then the Packet Scan is listening to that network interface and doing all of the analysis that way. So whether you deploy it at the controller working position or at the radio station or anywhere in the middle, honestly, anywhere where it can capture traffic, you can place packet scan there, and it'll do the full analysis of the ED137 calls. Now, they can actually work together. So you can have multiple packet scans deployed across your air traffic network. Hundreds of packet scan probes can be deployed throughout your air traffic network, and they can all send the results back to a centralized system, which we call Net Surveyor Web. It's a centralized database. And so the packet scans are, you can think of them as remote probes out on your network at different places, but they're all sending data back in real time to your centralized database, which we call Net Surveyor Web. That's how we do monitoring. It's very versatile. We can be anywhere in the network, in the wired network, capturing the traffic. Okay, so the packet scan software has a very easy to use graphical user interface. It actually kind of looks like Wireshark if you're familiar with Wireshark. And you can click on any packet, or you can click on any call detail record, and you can get basically the full decode of that call. You can get all of the basic Ethernet and IP information. You can also get the whole ED137 information. So we see here things like PTT type, squelch, PTT ID, PTT mute, and then you get the values on, off, and so forth. Simultaneous call transmission and all of these different values. In this case, they're set to 0, but for any given call, it'll decode all of that information and present it here for you. So we can go real in depth at the packet level and decode every single byte in the packet. You can analyze the traffic online or offline. So if you want to save the packet captures, you can do that. You can save them in PCAP format. You can save them in our proprietary HDL format. And then at a later time, you can open up the packet captures and do the analysis. Or you can analyze in real time as the traffic is going across the network. Okay. Packet scan, like I mentioned before, it can be deployed on a specialized hardware platform that we provide, so that you can do long-term captures, and we can customize the amount of storage in the system: 1 terabyte, 2 terabytes, 5 terabytes. We can increase the storage quite a bit so that you can do long-term captures and save all the information. The previous screenshot showed the packet level. Here I just want to go over the actual call detail, the call level, the call summary level. So it will intelligently group all of the packets into calls. And for each call, you can click on the call. You can see information like the mean opinion score in both directions. You can get stuff like the packet loss, the call duration, jitter, and other types of packet metrics. You can see the whole call setup and teardown just like you can in the Maps software. You can do it here as well. You can record the call. You can play back the audio of the call, detect all sorts of inbound and outbound digits and tones. You can trigger on certain calls of interest, so you can have alerts pop up on the screen when a certain call of interest is detected, maybe a certain IP address or maybe a certain voice quality score, something like that. If you're particularly interested in, you can set up a trigger and it'll show the alert in the alert summary right here. That's another key feature. If you can imagine, if you're monitoring thousands of calls, but you only want to get an alert when a certain type of call is detected, then you can set that alert up and then just quickly go to the alert summary tab and see when that trigger fires. You can log all the call details to CSV files as well. So here we're showing a bad call. So here you can see how in one call there was missing packets, and because there was a missing packets, the mean opinion score was quite low. And now here we see a good call where there's no missing packets, and the mean opinion score is therefore quite high. So this is all viewable through the Net Surveyor web browser that I'm going to show on the next slide. So now this is Net Surveyor web here. This is the web. This is the centralized database that I mentioned, and the nice thing about this centralized database is that it comes with a browser-based user interface. So here is a little snapshot of this web-based dashboard. Everything that you saw on the previous screen in Packet Scan is also viewable here in Net Surveyor Web. So you can click on any given call, all the same information as Rob mentioned, it's all here. The missing packets, the mean opinion score, it's all here shown to you in this centralized web-based dashboard. So if you have multiple packet scans deployed across the network, you can get information from all of them, and it's all displayed conveniently in a web-based dashboard. And because it's web-based, you can log into this web-based interface from any browser anywhere that has an IP connection to that centralized database. You don't need to be at that centralized database. You can be anywhere in the network and just browse to this web page where you can see all this information. Without getting too much into the weeds, you can set up filters. You can look at certain you can look at different days, different hours. You can look at different reports. Here again, from the centralized web-based dashboard, you can see the call setup and teardown. You can see all of the events taking place in the call, and so on and so forth. So again, you can all the information that you can see from Packet Scan or Maps, you can also see from the Net Surveyor Web dashboard. You also here on the left-hand side, you can see that we can categorize it by air-to-ground calls, ground-to-ground calls, good quality calls, poor quality calls, failed calls. There's actually more metrics that you can define, and it'll show up here. And lastly, you can get customizable graphs on the calls. So you can see, like here, we're showing the answered calls as well as the failed calls for each day. So you can get all the information on all the calls. You can summarize it, get pretty graphs, export the graphs to PDF. You can do all of that. You can look at different voice quality scores, and so on and so forth. Okay, so now I will turn it over to our next presenter, who will talk about delay and voice quality measurements in these ED138 standards. So Nagaraj, feel free to go ahead.
Thanks, Vikram. Hello, everyone. I'll be introducing you all to GL's critical time delay and voice quality measurement solutions. So as per ED138 performance matrices, there are some delay and voice quality requirements defined by the air traffic, which have to be met by the air traffic management network or the devices which have been integrated into the air traffic management network. Okay, particularly delay and voice quality, which are important with transition to IP networks. Okay, which will introduce packetization delays, jitter buffer delays, and other some other uncertainties. So GL's critical time delay and voice quality measurement solution is a test suite of equipments designed by GL Communications to calculate signaling delays, okay, to calculate the voice delays and to calculate the voice quality across the devices such as VCSs, gateways, radios, and across the other elements of the networks as well, and across end-to-end to the end-to-end network as well. So on the screen, what you are seeing is a typical ATM network, typical ATM network, which shows different elements in the network, different elements in the ATM network, comprising of both legacy as well as VoIP devices. So, for example, in an essential scenario, to measure the PTT delay, okay, between, that is push to talk delay between controller working position, okay, and and the VoIP network. So here are the different timing points of a signal or a voice event at different probing points in the network. So we should be able to, using the GL's test suite, we should be able to calculate delays across the devices and delays across the network as well. So we need to on the screen we can see that T0, T1, T2, and so on. So these shows the timing references of an event at different points in the network. For example, T0 is an PTT event which has occurred at the analog endpoint on the far left hand side at the legacy VCS, and we would be having one more reference at the T2, okay, which is a timing PTT event detected on the VoIP line, okay, which has been probed through the VoIP traffic, which is which has been extracted through the ED137 headers on the IP traffic. So this slide lists some of the important events, okay, which are for which the delay calculation is important. So for example, few of the events are PTT confirmations, squelch events, end-to-end voice delays, transfer delays, etc. So on this particular slide, okay, we are showing how our test suite of equipments are integrated into the ATM network to simulate analog endpoints, to simulate the VoIP endpoints, as well as to probe and precisely timestamp the events at different points in the network. Okay, on the far left hand side, we can see the audio analyzer. Okay, the audio analyzer, which has a capability to simulate push to talk and insert voice into the VCS at the analog interface. So, and we can see the packet analyzer, okay, which is sitting in line between the VoIP endpoints and has a capability to filter, it has a capability to filter and precisely timestamp at the line rate. So it is going, it has along with sitting between the, it is sitting with all the events probed and timestamped by the hardware at nanosecond precision. So our devices support time syncing using the GPS for in case if the probing points are geographically apart, okay, else devices support even the time syncing using the daisy chaining mechanism when the probing points are within the lab environment. So next device is event data logger. So event data logger is a centralized device which can collect all the events which have been filtered and forwarded, okay, from the different probing points, okay, and in turn we do have one more application called GUI based maps administrator, which is a GUI based client which orchestrates the entire test scenario from the point of the emulation till the point where it is going to be it is going to be probed, and probed event time stamps can be stored into the maps administrator, and in turn delay will be calculated between the two events. So GL meets all the critical specifications for ATM delay and voice quality measurements.
All right, thanks, Nagaraj. So this is voice quality. So part of what Nagaraj was saying, this whole time critical delay testing and so forth, as part of all that, we can also send audio across the network, whether it's going over VoIP or going over the legacy. We can send voice and record voice, and then we can take that recorded voice and analyze it against the sent voice using either the Polka algorithm, which is ITU 863, which is the latest algorithm, or we can also test using the PESC algorithm, which is ITU 862, the previous algorithm. Both algorithms provide a voice quality metric or a mean opinion score of 1 to 5, and that'll give you an idea of what the quality of the audio was. So this is part of our overall testing, end-to-end testing, for testing your network, testing the legacy to VoIP or VoIP to VoIP or whatever you want to do. This is the hardware that's associated with the overall testing for this critical time measurements, this overall testing. So there's the Maps admin, as Nagaraj mentioned. That's just a regular PC, and then we have the packet analyzer, the audit, which is actually giving you some time measurements. That uses our it's a 1U rack that uses our packet expert. Then we have our audio analyzer, which is sending and receiving audio, also controlling the PTT on the network. Again, a 1U rack using our dual UTA hardware, and then the discrete signal logger. Again, a 1U rack using our packet expert. So these devices would be in the network to test this whole critical time delay measurement. This is a rack system. We also have this available in a portable solution. So these units or these devices can be in portable PCs that can be deployed very quickly to a network and then moved around, whatever you want to do. Next slide. That concludes the presentation.
Okay. Yeah, thank you everybody for attending the webinar today. For more information, if you have any specific questions, please feel free to email us at info@gl.com. Thank you, and have a good rest of your day or night or wherever you're dialing in from. Please enjoy the rest of your day. Thank you.